As we go into the last few topics of our course, in Chapter 9, Section 1, we're going to take a look at probability. So an introduction to probability. Here are the objectives. Again, you might pause, but we'll be going through these item by item. Now, as we look at background, what's another word for probability? Well, chance. The chance that something would occur. And as we go to study it, you think of what events are possible. And we'll get some background here as we go on. And the simple thing about probability is the event that you're looking for here. And by the way, when we work with probability, we think of it as sort of an experiment. And when we think of all the things that could possibly happen in regard to that particular experiment, here's another key word. We think of that as the sample space, and that the item we're thinking of occurs, we're thinking of that as the event. So as we do trials, another key word here, our sample space is all the events. Should put an S there. Sample space. Now, in the Venn diagram, and sometimes this is related to that, the universe is in a sense your sample space of the experiment or the events that you're thinking of might happen, and then that a particular event would occur out of the possible kinds of events related to that. This is a ratio that's often given as a percentage, and this is what probability is. Now, we're going to take a look at this in a little more detail. And an example that's so often used in describing probability is a coin. That one side of the coin is a heads, and on the other side of the coin is a tails. So the probability that a heads would occur when you randomly flip a coin, and here we're talking about random events, events that are not for sure going to happen, but where there's a variety of events that could happen. And if the coin is tossed honestly, that is, without prejudice in terms of setting it up so you know the outcome, the probability of getting a heads would be 1 out of 2 possible events. The probability that you would get a tails is 1 out of 2 events. Now, the general rule is if you add up the probability of your events occurring, it should equal 1. So that an event was always going to happen, the probability is 1. That's 100%. Now, the probability that something would not happen, that it couldn't happen, we say is 0. So generally, probability is greater than 0, but less than 1. Not happening ever would be 0. Always happening would be 1. So probability is built in between there. All right, so in summary, as we look at what probability is, we think of a trial is a repetition of the same procedure. The outcome is the results. You measure and keep track. The sample space, again, they're describing it as a set of all potential outcomes. And then an event is the set of outcomes. So words. And again, we'll build on this as we go through the examples. Now, example 1, in a sense, we've used this as our background, tossing a coin. Toss a coin and observe the outcomes. Have we met the 3 conditions of a random experiment? Do we know ahead of time what's going to happen when we shake or flip a coin and see the results? No, that makes it random. The outcomes is unknown before the toss, and a sample space can be specified and in a sense contains 2 outcomes. So our sample space is the heads, tails. Now in example 2, we're tossing a coin 3 times, and we're wondering, does this meet the criteria? And yes, it's random. We don't know the results. And what is the sample space? Well, here this gets sort of a little bit tedious. What could result when you toss a coin? Well, the first coin toss could be either a head or a tail, so that's 1 out of 2. The second coin can be tossed and you get 1 out of 2. And the third coin tossed, you get 1 out of 2. So the probability now of how many different possibilities can you have is going to be the product of this, which is 1 out of 8. So there's 8 possible events. Now you start to think of them, and they have it laid out for us here. And I would suggest you actually copy down this, for example 2, as the sample space, again, the possible outcomes. Well, here we see we're going to get 3 tails, 2 tails and a head. Now notice this is 2 tails and a head, but the order is different as you do them. And then a tail, 2 heads. Now a head and 2 tails. Head, tails, heads. 2 heads and a tail. And then 3 heads. These are 8 possible outcomes. So the probability of any one of these outcomes in this particular order is going to be 1 out of 8. Now, other times we'll be asked the probability of getting 2 tails, and then you would physically count them, but you would have to know what your sample space is. Now, what was the question they asked? Toss 3 coins 3 times, observe the number of heads. So as we pick up down at the bottom, if in the specifics you wanted obtaining more than 1 head, you would look through your sample space and see you would get 1, 2, 3, 4. Half of the time you would get more than one head. Another kind of example they often use when we are dealing with probability is rolling a die, for example, 3. Now, what is a die? Well, it's a single member of a pair of dice, and it's a cube, and a cube has 6 sides. So what will the sample space be? Well, they're picturing it down below and also listing it. That is a 1, a 2, a 3, a 4, a 5, a 6. So that you would get any one particular outcome when you roll a die. And I think a little sketch might be useful, or at least a sample space. And what would the probability be of rolling an even number when you roll the die? Well, again, you would look at your sample space, and that would be 6, and that the number would be even. The numbers even are 2, 4, 6. There are 3 that are even. So this would result in the probability of 1/2. And that's the example they're looking at here. Again, in reflection, so far we've talked about the probability of tossing a coin with 2 sides, rolling a die with 6 sides, but another major area of probability is a deck of cards. Now, I don't know how much you know about cards, but they will be using cards in our probability studies, and you need to be familiar with them. First of all, within a deck of cards, there are 4 suits, as we call them. They would be 13 hearts, and these are what the hearts look like. They have a picture of a heart on them. 13 clubs, and the clubs are these. 13 spades, and they look like a shovel sort of sense, and then diamonds, which are pictured here. Now, within each suit, so if you added these all up, by the way, you get there are 52 cards in a deck made up of these 4 suits. Now, within the suits, you have an ace, and then you have the numbers 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you have a jack, a queen, and a king. Now, the jack, queen, and king are called face cards. And they have each of this illustrated in each of the suits. So, when you're dealing with probability of playing cards, it's out of 52 that you're going to get on a particular selection, or when you shuffle and deal the cards, that you will get a particular card. Then that would be your event you're looking for out of the possibilities, and this gives you a probability. Again, and then some of these get quite tricky here. Now, in the case of getting any particular 5 cards in the deck, that probability gets up there quite a bit. I know I like to play around with solitaire as I do things, and that's sort of interesting here. Now, continuing our introduction of probability, we're looking at a key word, and we'll want you to put this in your notes as background, and that is empirical probability. Now, empirical probability deals with a particular event. One that I've seen used in other courses was to take a styrofoam cup and then toss it. Will it land on its bottom? Will it land on its side? Or will it land on its top? Now, tossing this cup, let's say for 100 times, you're going to see the results of this experiment, and the collection of the probability of the sum of these events would be considered empirical probability. Now, there's another kind that we'll be talking about, and that is theoretical probability, and we'll get to that in a little while. So, for instance, if you toss this styrofoam cup 100 times, and 10 times it lands on its bottom, 82 times it lands on its side, and let's say to make this would be 8 on its top. That would add up to 100. Now, you might do this a number of times, and the results would not be quite the same, but for this 100 initial tosses, this would be your probability. And when you do an experiment this way, this is referred to as empirical probability. Now, here's the formula, and it wouldn't hurt, of course, to write this down. Example 5. Here we have a basketball player throwing free throws, and the sample space would be 420, and the number that was made, what we're looking for, was 300. And you could do some simplification. This ends up being 5 out of 7, which I believe is pretty good ratio, and it would be this percent. Now, what would be the probability he would not make the baskets? Well, you would subtract this from 1, and you would get 2 out of 7, which is what they're showing down here. All right, pause, take some notes. Again, this is empirical probability. In example 6, and again, you want to keep track of the numbers. Here, a drug company is testing a diet pill, and there were 500 in the group that they worked on. So if we added all these up, this would be 500. Now, to figure any of the probabilities, one event would be they lost weight, another would be the weight stayed the same, and then in a third, they gained weight. So again, depending on what you are wondering about, it would be this amount over the 500 for each of these things. And that's what they have listed here. So let's take a moment to note the results. That patients lost weight, And again, 50% having something, and is that a significant difference? Again, we're not analyzing that. And then others where the weight stayed the same. Or lost weight. Or as they look at it in part B, the patient does not gain weight. So again, you would add lost weight, stayed the same, get that ratio, and then convert it to a percent. So again, another example of empirical probability. Now, in example 7, we're doing what is called empirical probability. Here, a casino wanted to assess new dice, so they roll one of them 1,000 times. So again, your sample space is 1,000. And then they got a 1, a 2, a 3, a 4, a 5, a 6. And then putting this all over 1,000, they got their what are called probability distributions. And again, I don't think you need to write all this down. It's just another example of it. A question we might ask, if we added up all of these frequencies here, what would this add up to? And it would be 100 out of 100. Because again, the total that one of these events would occur is going to be 100%. These are the only possible events that could occur. All right. Now, up over here, there should be a circle with a letter I in there. If you click on this, it shows some of what I did when I was a high school teacher in my biology days, where we used probability in regard to biology. And of course, that was one of the major areas in genetics, our study of heredity. Now, looking at the other kind of probability is if we make a little chart of our heads and tails that we mentioned earlier, and you might sketch this out. You could get a heads, you could get a tails, you can get a heads, you can get a tails, and then you fill in this little chart. There's two heads, there's a head and a tail and a head, and a tail and a tail. Now, mathematically looking at this, what is the probability that you're going to get two heads? Well, there are 4 possible events. 1 out of 4 gives you a 25% probability. Now, did we do that by flipping the coins or by analyzing this mathematically? And the answer is by analyzing it mathematically. Well, this kind of probability we think of as the classical approach. This is classical probability, where we figure something out mathematically. Another word we use for this in biology is hypothetical probability. That is based on the math. Now, when we observe things and do the counting, that is empirical. Hopefully you get the distinction of it. Now, the formulas are similar, and you see it written down here. So again, this is the formula for classical probability. Take a moment, write it down so you know what the letters are and what they're referring to, and the formal way of showing it. Going on to example 8 now, we're going to use that die that we had, roll it. What's the classical probability of getting a 5? Well, we said there were 6 sides, so getting a 5 would be 1 out of 6, and then that probability rounded off is this. And again, here you're figuring things out mathematically, as opposed to earlier when the casino did its rolling of a die and keeping track of it and getting the empirical amount. Now, one of the things they slipped in here, and I didn't mention that strongly, is when you roll a particular die, and you should get a 5 1 out of 6 times, you might roll a die 10 times and not get a 5. So what's going on? Well, with small amounts of data, it doesn't necessarily approach the expected results. We talk about the rule of large numbers, that when you flip a coin, you expect that half of the time you're going to get heads and half of the time you're going to get tails, but you never know what you're going to get the next time if it's an honest throw. It's just the rule of large numbers that you approach what you would expect. Now for number 9, we're dealing with our deck of cards, and there are 52 cards in the deck. What is the probability of getting, let's say, a heart? Well, 13 hearts in the deck, 13 out of 52, that would be 1 out of 4. So again, this one was sort of easy, and again, you're hopefully developing a background. For number 10, we did some like this earlier, where we listed the probable outcomes of tossing 3 coins at a time. What's the probability of getting at least 1 head? Well, you could look at it and see that the only one that didn't have 1 head was when there were 3 tails. All the others had at least 1 head. And there were 8 as our sample field. So this would be 7 out of 8, which gives you this probability. Now, they're going to accept probability in the fraction form, also in the decimal form. Now, as we approach the end of these, they're asking us to develop what is called a possibility tree, where using something rather simple, and let's start to build this, we're going to have a head and a tail. Now, from this head, the next toss could be a head or a tail. And from each of these, we could get a head of a tail, head and tail, head and tail. And now, if you watch how as we go this way, we get 3 heads, 2 heads and a tail. Head, tails, heads. Heads, tail, tail. And then tail, heads, heads. Tail, heads, tail. Tail. I'm forgetting this one. Heads, tails, heads. Tails, tails, tails. Now, each of these outcomes are equally likely, but this shows our possibilities. Being able to make a chart like this is a useful tool because you could easily substitute a boy girl for this, or any two items that you're going to do 3 times to get what the profile of the results would look like. Now in number 11, they're using a tree diagram to calculate classical probability. On your way home from work, you encounter 4 traffic lights. Assume the lights are equally likely to be green or red. We assume there are no yellow lights. So make a tree. And again, this gets kind of tedious. Let's say you don't have to include this in your notes. Just sort of see how it goes. So there's the green, there's the red, and from this you can get a green, red from each of these. And where the other ones stopped here at the third, here we're adding a fourth, and we're getting more. So this would be how many possibilities? Well, it would be 1 out of 2 times 1 out of 2 times 1 out of 2 times 1 out of 2. It's going to give you 1 out of 16. So there are 16 combinations. And if they asked you to figure out any one of these as we look at this, what are the questions they're asking? Determine the probability of getting 4 red lights on your way home. Well, the only one that is 4, and I'm getting some strange results here, is this bottom one, which would be 1 out of 16. That you're going to get any one of these combinations in this order is 1 out of 16. That you would get all green lights would be 1 out of 16. So this is our last slide, which is a summary of what we've done. We've mentioned a lot of this as we've gone on, but let's see it summarized here. Rules of probability. It's going to be between usually 0 and 1. Not happening is 0, always happening is 1. And they talk about that here. And again, I think we've summarized this, and this is probably long enough. All right, let's go on to our next section in a little while, and we'll wrap this up.